Hey all, hopefully you are all back. So, who is not convinced that this attack can work? So, questions, do you think what could be the problem? Do you see any issues, something that is not clear? Weights and layers, yes. So, for both weights and layers, we do CPA, correlation power analysis. And like I say, it's just perspective how to do it. So first, in the attack, chronologically, what we need to do is to recognize the layers and think of it in a very simple way. So you have a number of neurons. Let's say there are 10 neurons. You know when is your algorithm starts to run. So you do measurement from beginning of the algorithm. At the beginning of the algorithm, you know you are in the layer 1, because that's the first layer. And then if you are in the layer 1, you take the information about the first neuron, this is what you can recognize, and then you say this neuron is in the first layer. And you challenge that with saying, no, this layer is in the second layer. You do the correlation for all the weights, you will get either higher value that it is in first layer or higher value that is in the second layer. Once you are done with that neuron, you will go for the next neuron. And depending on the answer from the previous one, you know what to do. Because if the answer from the previous one was its first layer, well, you know then this was not the boundary. Then you do the second neuron. You again ask the question, is it the first layer? Is it the second layer? If you get the answer, it's the first layer, you do not draw that red line. You continue to the third neuron. You again ask the question, is this neuron first layer or is it second layer? If you made a mistake, you go back. No, there is no going back. There is, hopefully we do not make mistake. We start with the layer 1, with the first neuron. We know that must be layer 1. There is nothing before that. And then we ask, is this first or second? Of course, we know the answer will be, this is first. Then we do the second neuron, and then we ask the question, is this first or second? If it says it's first, we say fine. If it says second, then we just mentally draw a red line between the previous neuron we processed and this one. And we say, okay, this is the layer between, this is the boundary between two layers. And then whenever we process every consequent following neuron, we do not need to ask, is it first or is it second? Because the previous neuron was already answered, okay, this is the second. So now the only question is it the second or is it the third? So think of it from this side. You ask the question, is it first layer, is it first layer, first layer, first layer? At the moment when you get answer, no, it's not first layer, you say, okay, this neuron is the first neuron of the new layer. And then you continue. At the moment you get answer, no, this neuron is not in this layer, you say, okay, that neuron is the first neuron of the next layer. And then you continue. So you do not never need to go back. You will always know what is the correct layer for that neuron. Is it at least a little bit more clear? So it's very simple. You know it must be either A or B. If it's A, you say fine. If it's B, you say I draw a line before that neuron and I start again the game. I just now ask not first, second, but second and third. At the moment you draw a line, well, not second and third, but third and fourth layer. You are just mentally drawing lines whenever the second hypothesis gets higher correlation. So if I'm a resident 50, how much time it takes for you to crack me? That is very difficult question. I would say impossible to answer because Resident 50 cannot be implemented on a microcontroller. So I would not know in this context. So we would need also to go to more serious devices like I don't know, like GPUs. And then first I would need to know exactly what kind of GPU is to just know what is the number of measurements I need to acquire to be able to break it at all. Every neuron on the same layer consumes the same, right? Or you do not assume it. Well, we do not assume consumption. We just assume the multiplication with the weight, and we see what kind of correlation do we get. Do we get higher or lower correlation for when we multiply with every possible weight? I talked about the computation. Well, hmm. Yes. Well, yeah. Let's say like something like that. In fully connected dense layers like MLP, that's easier to know than what happens in convolution layers. But yes, yes. Let's say it would we would assume it kind of consumes more or less the same. So maybe it would not be completely the same because it also has difference because depending on the weight of that neuron. But we are somewhere talking about that. Why are we assuming there are no mistakes? Well, we do not assume there are no mistakes. We just say we don't care about mistakes. We are doing our best. Whether we made mistakes, that will be clear in the end when we are trying to reverse engineer. So this is again the same. How do you do side channel on AES? You can also assume there are mistakes there. How do you know did you do mistakes or not? Well, once you recover the whole key, you will try to decrypt with that key. If it decrypts into something reasonable, you will say, well, I did not make mistake. There is a chance to make a mistake. You never know that. Might it be better maybe use something like HMM that maximize the entire probability? What is HMM? Hidden. Okay, then I was thinking correct. um, I don't know. This is a question I do not know answer because it could maximize the whole probability, but I cannot say it would work better because I never tried it in this context, so I have no idea. In essence, you would always wanna start with the simplest thing, and correlation power analysis is basically as simple as it gets when talking about direct attacks about breaking targets. So CPA, SEMA is basically as simple as it gets. So the natural step for anyone would be to go into that technique before going into more complicated techniques. So yes, maybe you could make better, more powerful attacks, but that's not a natural way how security analyst would work. You would start by doing the CPA, and then if you can break it with CPA, you would say, well, this device is obviously not secure or not secure enough. If you are not able to break it with CPA, then you would assume more complex attack methods. But you would always start with something simpler. So I will continue how to extend this attack for RNNs. I have many ideas. None of those ideas really worked. It's actually possible. The biggest problem is that our beginning results that we did with RNNs, they just took so much more effort in the number of traces. So in essence, you could do measurements, you could recognize stuff because you can also recognize the difference between convolution layer versus pooling layer, all that stuff that's doable. So the same concepts for RNNs, so let's say sequential models, but then the effort is quite huge. So I would not directly know how to extend it in the setting to tell you use just and exactly this and the attack would work. So I do not actually have good answer to this. But it's a question that we discussed quite a lot of already, and we are thinking, well, this is something we need to do in future. But now it's more on engineering than on scientific approach. Now it's just more measurements, more signal processing, more this, more that. So let's say you are all convinced that this attack is possible. So hopefully I was convincing enough to explain this. And I will now just briefly in 2 minutes tell you that you can do also a nice extension of this attack, and then you can do recovering of the input of neural network if you know the model of a neural network. So now we are changing this setting. Up to now I said I know the input, I know nothing about the model. Now I will say I know nothing about the input, but I know everything about the model. And then everything is the same, so we still use Hamming-Weight model, or everything stays the same. These are just repeating just for the sake of the clarity. And we again attack the multiplication operation, because now we are trying to get the input. And of course, to get the input, natural point is to attack the multiplication, because now we know the weights, we just don't know the x. Okay? But actually, here is the problem. We know the weights, but x changes from every execution to every execution, because every input is different. Think of it in the crypto sense, every plain text is different. You don't do all the time with the same plain text. That would not make sense. So your input all the time changes. So for this attack to work, you actually need to do attack that can work with only a single measurement. So you need only a single measurement for your attack to work. How to do attack like that? Well, you do horizontal attack. So this is kind of advanced concept, but I will try to break it down in very simple terms that you at least have the perspective of what was it. So since we want to get the input, we know we need to look at the first hidden layer, because this is where input comes. And then we look at input multiplied with the weights that we know, one after the other. So if there are m multiplications, that means there are m weights in the first layer. And then we take that one trace, so many multiplications, and we cut that trace into many smaller traces, where each smaller trace will correspond to a single multiplication with a known weight. And then you get something like this. So we have a single trace, so there are 4 multiplications. We split those into 4 parts, and we align it like this. And now we have our x that is still always the same, but our weights are known. And then the attack is very easy to do, and you only need a single measurement to obtain your input. And you can actually see that the attack works better the bigger is neural network. Why? Could anyone tell me why this attack works bad when you have a small number of neurons, while it works much nicer if you have bigger number of neurons? So the same concept as before. Previously, we had many measurements, and we took those measurements. Now we have one measurement, and we cut it in many pieces. Why does it work better when you have more neurons? Trivial answer. Why does correlation power analysis works better when you have more measurements? Because you are able to get better statistical significance. The more neurons you have, the more multiplications there is. Exactly. There is more multiplications. And there are more multiplications means you can build nicer picture like this. There will be more pieces you can compare, and you will get the input easier. So actually, to recover the input, it works the better, the bigger the neural network it is. And actually, I will just show you the results. Again, cortex. This is the final result. Upper row are the original input. Lower second row is the recovered input. Can you see any difference? You can. I hope you cannot, because the difference are actually only at the second decimal places. Again, we played in the third decimal place, fourth decimal place, but in essence, we couldn't see anything by the eye. And one can ask, why are there no numbers 8 and 9 here? The answer is very easy. Could anyone assume what would be the answer? Slide is too narrow. Exactly. Exactly. So I did not have enough space on the slide to have 8 and 9. Nothing else. But it works also for numbers 8 and 9.